The science research that is underway on board the International Space Station covers a wide range of disciplines. We talk most days about the work that's being done to protect the astronauts. There's also a variety of other sciences, things like astronomy and biology and physics. And there have been a series of experiments that have taken advantage of the weightlessness of space to investigate the behavior of colloids. And one of those experiments is known as the InSPACE experiment, and it was recently featured in a Science at NASA article about the development not of smart materials, but in fact of genius materials. The principal investigator on InSPACE is Dr. Eric Furst. He joins us this morning from his office at the University of Delaware. Dr. Furst, good morning. Would you start by giving us the short version of what a colloid is and how you got interested in researching them in the first place?
Sure. Good morning, Pat. Colloids basically refer to small particles dispersed in a fluid. These particles are on the order of maybe tens to hundreds of nanometers to micrometers in scale. It refers to a unique length scale of matter where the material is many billions of atoms still in size, and yet small enough, so small that you'd have to use a microscope to see it, or even more exotic techniques to see the particles. But what that does is it confers certain properties on those particles, and one of those special properties is that they exhibit Brownian motion, random thermal motion, and that gives them all sorts of really neat things that we use in technologies and we like to study in some of our scientific work. Why I'm interested in colloids is because they're really interesting building blocks of matter to assemble other structures from, or other useful functional types of materials, genius materials as some people have called them. Mm-hmm. And those actually span a wide variety of things that we can imagine we would want to use technologically in the future, as well as lots of things that surround us today. Many of the consumer care products that we use are actually structured on this length scale. They're actually colloidal materials. The shampoos that we have, detergents, fabric softeners, paints, these are all colloidal materials.
And you've been investigating with the InSPACE experiment on this space station as far back as Expedition 6. Have you been looking at the same thing in each iteration of this?
Well, not quite.
Okay.
It has been a while since we kicked these off, and actually some of these the experimental ideas stretch back to even when I was doing my PhD with my advisor a number of years ago. It's part of the iterative aspect of science that every time you ask a question and you start to answer that, 10 more questions come up as you peer into this sort of frontier between what we know and what we don't know, and that can really lead to some exciting work. That's what's happened here in the InSPACE experiments. When we first started off, we were looking at just the structure of these materials under magnetic fields, and we got some ideas about how we might be able to change or tailor those structures that would give us insight into how we can make new materials here on Earth, and that's what led to InSPACE 2, and from that, that's grown into an InSPACE 3 project.
What did you think was going to happen when you applied a magnetic force to colloids?
Yeah, so these specific experiments look at some special particles, basically. These are colloids that are magnetically responsive. And for us, they're mainly model materials for work that we do here on the ground, where we use electric fields to guide the assembly of particles, directed self-assembly. Anyway, these magnetic particles respond to the magnetic field, and we know a lot about that from ground-based experiments. If you place a magnetic field on one of these, they're fluids initially, just like a dilute paint. If you took a latex paint, they would flow like that. But when you put them in a magnetic field of sufficient strength, they freeze up. They become a solid. And so on Earth, there's technologies based on that called magnetorheological dampers, and that transition from a liquid to a solid is called the magnetorheological effect. So we were pretty sure that we would see that effect, that we could form these sort of solids in space. But what we were really interested in the experiments was, well, what would happen if we turn that field on and off, toggle that field on and off? Would the suspension structure change? And in fact, it does. That's the study that we initiated, and we were looking then at how these structures coarsen with time. That gives us insight into how those materials are assembling and forming essentially an equilibrium structure that's dictated by their shapes and their interactions. And that's really the basis of these sort of materials that form themselves, what we call self-assembly.
What are applications that we might understand for how that could be used to our advantage, either in space and on the ground?
Yeah, so I mean, in my laboratory, we've used this sort of self-assembly principle to make materials with interesting optical properties that might be useful as color displays, for instance, like electronic inks. We've made materials that have ultra-low thermal conductivity, so that they're nice thermal barriers. That would certainly have applications in turbines, for instance, here on Earth, gas-based turbines, aircraft turbines, as well as potential space applications. The ability to structure matter and actually get that structure to form on its own spontaneously gives us new manufacturing methods for nanotechnology. So that's one of the things that we're really interested and excited about. And getting that structure to form, it confers properties with how that material is going to interact with energy, how it's going to interact with chemical species, and so there's many facets that can have an impact. And again, sort of we use materials like this on an everyday basis. So it just shows the sort of breadth of what can be impacted by that.
I suspect that there might be more worthwhile research to do. Is there going to be an InSPACE 4?
I hope so. We have, like I said, every time you ask a question, you get at least 10 more back. We've discovered some really interesting things in these last experiments based on how we can change the shape of the particle to guide different structures to form. And we've been doing corresponding experiments here on the ground. There's a lot of things that we would like to try, and with some of the facilities that have been sent up and have been developed on the space station, it's really just such a unique laboratory for us to access and to use. It's a phenomenal research activity, and having, one of the really key things is taking advantage of the microgravity for us. But also having the hands of the astronauts on those experiments, that feedback that we get from them allows us to take advantage of that really unique environment in space, but in a much deeper and richer way, I think, than if we could just send an automated experiment up. It gives us that feedback loop and that observation and that control that humans have in the laboratory. So I hope we can take advantage of that some more.
We'll look forward to seeing it. Dr. Furst, thank you very much. We appreciate talking to you this morning.
Thank you. Have a great day.
Dr. Eric Furst is the principal investigator of the InSPACE experiment, which has been underway on board the International Space Station now for a number of years.